Hey everybody, welcome back to webinar number 2 of our lunar webinar series. We are joined again with Jim Woodburn, the Chief Astrodynamicist of AGI, and astrodynamicists John Carrico and Mike Laux from Space Exploration Engineering. And all these guys have worked a lot on lunar missions already. If you want to learn more about space exploration engineering, you can go to see.com, see.com. And if you want to hear more of the things that Jim Woodburn has worked on, you can check out agi.com. There's some of his papers and things are up there as well. So today we're going to be continuing this lunar webinar series. And last time we talked a little bit about why lunar missions are different. So welcome, guys. Welcome back.
Yeah, thanks. Yeah, and I think one of the most important things we uncovered in the last one about why lunar missions are different was, well, about the restaurant on the moon, right, Josh?
I haven't heard that one.
What about? We went into it in depth in the last one. So the restaurants on the moon, they have great food, but no atmosphere.
Yeah, that's great.
Just wanted to make sure no one forgot that.
Yeah, just keep that. Yeah. It's going to be in the show notes if you get that, if you want those.
Yeah.
So I'd sing it, but everybody would instantly sign off the webinar. But today we're going to be talking about flying to the moon and all the different types of trajectories and strategies for getting there. Right? Is that right?
Yeah.
And I just wanted to, in your vast lunar history, bring up the fact that you guys were directly involved with what I have called before the first commercial use of the moon. And can you go into a little bit about that, John Carrico?
Yeah, so you're talking about the AsiaSat 3 rescue mission.
Absolutely.
Which used the gravity of the moon as to move a commercial spacecraft into a useful orbit. But we've been using the gravity of the moon to create tides for a long time, and I've imagined that there's commercial uses of the moon for tides, because you can, when the water goes out, you can get the clams out of the ground when the water goes out. So it might not be the first commercial use of the moon now that we think about it.
And maybe like taking photographs of the moon and selling them.
Singing songs about the moon, writing songs and selling them.
Surf resorts, probably. So
using the moon, yeah.
All these years I've been incorrect saying that you guys were the first users commercially of the lunar gravity, but I'm going to keep saying it because it's
maybe
cool.
It's a satellite.
Well, yeah, all those things didn't use gravity, though, right? I mean, the tides do, but those other things.
That's true. That's true.
Yeah.
You're actually referring to the AsiaSat 3 mission that flew in '99. Now, I didn't have anything to do with that. I think, John, you were peripherally involved in that mission, right?
Yeah. We had. I just joined AGI, and before we had the Astrogator product, we had the Navigator product, and Cesar Ocampo had a demo disc of Navigator and started using it to plan that trajectory. So I went out there to watch him use Navigator and went to the control center, and that was super exciting. But it was a satellite that was supposed to go to geostationary orbit, and the upper stage didn't quite work. So they designed a trajectory to fly it around the moon and use the moon's gravity to bend the orbit so it can come back near the Earth's equatorial plane.
Very cool.
Yep.
So today we're going to go into a little bit more of the missions, all the different types of missions and trajectories you can use to get there. But real quick, again, I don't want to go into the deep history of it, but you'd mentioned Astrogator and you'd mentioned Navigator, but both of those actually grew out of software that you wrote before, which is a NASA product called SwingBy.
That's right, called SwingBy. Back, we started it in 1989, and the first mission we flew with that was Clementine, which is also a lunar mission. It was designed to support lunar gravity assists and things like that, but then Clementine came up, and that was a mission around the moon, and they did a bistatic radar test that was consistent with showing that there was water on the moon. And then the Lunar Prospector mission and the LCROSS mission were all showing things that were consistent with water on the moon. And the reason water is important is for several reasons. One is you can use it for fuel by breaking into hydrogen oxygen. So if you had a rocket that looked like this, then if you put water inside of it, then you could use it for fuel. Or one that looked like that rocket that Mike has.
There's a rocket right there that used hydrogen and oxygen.
Hydrogen and oxygen. The other thing I wanted to demonstrate that you can do with water, if you were living there, is you can drink.
No, we got to make sure we rep all the different launch fields. You got your SpaceX. I got my Rocket Lab here. Here we go.
Okay. Does that have rocket fuel in it too, by the way?
It does. Yeah, it does.
Okay. Okay. So we now know that at least 2 rockets can be done that. And then you can also break it down and breathe the oxygen. So commercial use of the moon, as we were talking about, would be to go to get the water out of those perpetually dark craters and sell it either in water bottles or in a rocket fuel gas station.
Perfect. And so you have a scenario that you're going to be walking us through that you guys
Yeah.
built with those tools to highlight a bunch of the different times and durations and trajectories, right?
Yeah. So this is a trajectory. This is a simplified trajectory going from the Earth to the moon, and we're showing this in the Earth-Moon rotating frame. It actually looks pretty similar in the Moon inertial frame. This is a southern approach where we're coming in under the south pole of the Moon, doing a lunar orbit insertion maneuver here, which is a retrograde maneuver, so going opposite the velocity of the satellite with respect to the Moon, and then capturing here into a circular orbit. And again, this is a simplified version. We'll go into some more details at a later time. And this one takes 5 days to go from the Earth to the Moon. So if I can switch to this other window here, we're showing this in the Earth-Moon rotating frame. And this is a 5-day trajectory that goes from the Earth to the Moon. When the Apollo astronauts went to the Moon, they took 3 days. And so they're on this curve here. So they were doing that so that they didn't have to spend as much time in space, need less air and water and food, and they were afraid about radiation at the time. It turns out that if you go on a 5-day transfer to the Moon, you're kind of coming in opposite the Moon's velocity. So you're going out on this curve. It's a little hard to see in this direction, so let me show it in inertial. In the inertial system, you go out into this orbit that's kind of like an elliptical orbit, and then the Moon catches up with you. And it turns out that if you're in a 5-day orbit, a 5-day transfer from the Earth to the Moon, then when you come in, you're coming in kind of opposite of the Moon's direction, and then the Moon's gravity helps slow you down, and you don't need as large of a maneuver to capture on the Moon. If you come in on a 3-day transfer, you're kind of at an angle to the Moon's direction, and you need a little bit more delta V to capture on the Moon. And then Mike actually put this together. Mike, do you want to just describe this while I'm turning these on?
Oh yeah, I mean, all we're doing is showing the different types of transfers in terms of days that go to the Moon, and you can see in the component browser, an SDK over there to their left, that there's a 3-day one, which is the one with the least curvature to it, and that's the one that's interior close to the Earth-Moon line there, and that goes all the way up to a 7-day transfer. And you can see, in this case, all those trajectories are leaving the Earth, roughly at the same time, and then the 3-day guy, of course, will get there faster than the other guys will. But the interesting thing about this is, that this demonstrates to you, if you went in and looked at this, which we have, and looked at the difference in total delta V cost to get from the Moon to the Moon from the Earth here, the translunar injection delta V to come out of Earth orbit is something close to pi in kilometers per second, 3.14. But in the case of a 3-day transfer, you're only saving 16 meters per second to go to on a 5-day transfer instead of a 3, and the total in meters per second is 3,100 meters per second. So there's not, when someone talks to you about optimizing your lunar transfer, you're not saving a whole lot of delta V to do that. Of course, like John said, in the case of the Apollo astronauts, it was all about getting them there faster and also being able to do a free return. But but it is an interesting thing to think about, the nonlinearities of this, that if you're trying to go to the moon, the difference between a 3-day transfer and a 5-day transfer is on the order of the errors that you might see from a launch vehicle in the insertion that it gives you into your translunar injection itself. So when that's the case, when your insertion errors are enough to change your time of flight by 2 days, that means they're enough to make you miss the moon completely. So it's an interesting problem to have that you have to solve, that the errors of the launch vehicle, which normally aren't that huge when you think about them in Earth orbit, out here, when you're going to the moon, they're enough to make you miss completely. So you have to be able to clean those up.
And sometimes you want to bias it a little bit lower because you don't want to go too far. So you're kind of looking kind of a game of statistics and working closely with the launch vehicle to figure out really what side are their uncertainties on.
Well, there's a funny thing that this trajectory is showing here that John and I have run into a bunch of times over the years in creating trajectories, and that is, you can see that he's got some of the trajectories there that come in on the northern end of the moon, and some that come in from the south, and of course you can choose either side. But in the case that we chose, there's pathological cases sometimes where if you happen to go at the wrong time of the month, the moon's latitude is as high as it's going to get, which is near to 28 something degrees.
And you can see that here where these orbits are all, the latitude of the moon is really high. It's
and so in this particular case, we just happened to choose a month where the moon's latitude is really high with respect to the Earth's equator. And of course, the launch site that we're using at Kennedy Space Center ish is at 28.5 degrees. So you can find some cases where you can't actually get all the way to the moon coming out of that launch site. And John ran into a couple of those cases, and so he had to go under the moon in order to get there. Normally, you could also just fly a launch azimuth that gave you a better inclination, so you wouldn't run into this. But
yeah, using rough numbers, the Earth ecliptic is 23 degrees inclined to the Earth equator, 23.5, and then the moon's orbit is 5 degrees to the ecliptic. So sometimes you have the angle between the moon's orbit and the Earth is 23.5 plus 5 gives you 28.5, which is right where the launch pad is in Florida. And then the moon's just a little bit too high if you do a due east launch out of Florida. And you can't go into a northern orbit. If the moon is at its lowest latitude of negative 28.5, you might not be able to get the southern approach. But you just wait a day or two and then you can get there. Or you can change the inclination of the moon. And that if we do some lunar myth busting, you'll notice that when we launched out of Kennedy at 28.5 degree orbit. But when we got to the moon, we went into a polar orbit. It's a very, very loose coupling between the inclination that you're at Earth versus the inclination you go at the moon. So you don't have to be in a polar orbit around the Earth to get into a polar orbit around the moon. In fact, you can pretty much get most inclinations around the moon. The ones that are hard to get are the ones that are perfectly equatorial around the moon.
Well, the other thing that's important to note here too, John, back up so they can see this, but when we're transferring from the Earth to the moon, we aren't necessarily in the lunar plane while we're doing that. And so you can see that, there isn't any idea that you have to go in the plane. You can see our orbits are quite a bit out of the lunar orbit plane. They intersect certainly the plane of the moon when they get there, but the orbits themselves have not been lined up in the plane. Now, if you could do that, there's some advantages in terms of delta V, but the geometrical restrictions you'd have in order to make that happen are severe enough that you wouldn't bother. So like you say here, you don't have to be in the plane, and then you don't have to be what John said earlier, in terms of how you line up with it. So
yeah, so in this case, we're leaving the Earth, and we just give it a little bit of push, and it goes over the top of the moon. Yeah. And yet in these other cases here, you just aim at a little bit different, like shooting an arrow, and you're just going to aim under the moon, and then you go into that orbit.
Now, what you will see, while you're not constrained from getting into a polar orbit from anywhere, if you want to get into the equator at the moon, then that is a little bit more difficult. And there are times when you that when the geometry of, where you're coming from the Earth prevents that with any kind of low delta V weight. So equatorial orbits, which aren't as interesting on the moon as they are at the Earth, for example, are harder to get into because you have to go right when the moon is, when you have to intersect the moon at the equator. So that requires a particular geometry, and which means you have to get there a particular time of the month.
Yeah.
In order to allow that.
Yeah. And that brings up another point of lunar trajectories is when you land, if you're going to land at the moon, if you land on the near side, you can always see the Earth, but you might want to land when the sun is shining on that side of the moon so that you have power, because it gets really cold and a lot of the landers can't survive the lunar night. So when you go to land, you want to land kind of near the morning when it first comes into sunlight. And in that case, you just think of the moon's orbit as kind of like a clock. The moon's going, I guess it's going counterclockwise around the Earth, but it really is the phases of the moon. When you see whole moon, that's noon. When you see a full moon, that's, noon on the center of the moon. When you see the new moon and you just start to see the very beginnings of the waxing moon, the spots that you can see where the morning spots are. So there's, even though you can get to the moon on any day, you might want to get there when there's a certain lighting requirement to the moon. So these are classic, these are simplified, but these are classic direct transfers to the moon. On a lot of missions, like on the Clementine mission and the Laddie mission, we went into phasing loops before we did this final transfer. We can probably show that in another webinar. But this is one of the ways going to the moon, and like we said, the ones with the least delta V are usually between 4.5 and 5, maybe 6-day transfers, and those will be the least delta V to capture. They also tend to be very close to the minimum maneuver you need to leave the Earth as well. So that kind of lines up nicely, because you're pretty much just putting your apogee right at the moon's orbit. There's another way to get to the moon, and this is called the ballistic lunar transfer. Also, in the literature, it's the weak stability boundary transfer. So kind of zoomed out a little bit. So this is in the Earth inertial. This is where you leave the Earth and you have the rocket put you on a trajectory where your apogee is about 1.4 million kilometers away from the Earth. And as you fall back towards the Earth-Moon system, your perigee magically rises so that it gets above the moon, and it actually doesn't magically rise. Let me show this in a different coordinate system. This is in the inertial coordinate system, like the ICRF or J2000 system. If you look at this in the Earth-Sun rotating frame, so here's the Earth. That's again where Josh's friends live, is on this planet. And you draw a line always to the sun, which is this yellow line to the left. And again, the moon moon's orbit still looks pretty much the same. The same trajectory now looks like this. And as we fall back towards the moon, the sun's gravity is actually raising the perigee for you. So it ends up saving you propellant, and you can come in and you kind of co-orbit, and you're slower when you get to the moon. And it's very, can be like up to 10 or 20% less delta V to capture and orbit around the moon to get to the same orbit. And so this is a ballistic lunar transfer. The BLT orbit, as our friend Jeff Parker says, the bacon, lettuce, and tomato sandwich reminded him of the pork chop plots that you see for interplanetary. So calling it a BLT was somewhat appropriate. Just asked him about that last week, by the way. So, and this trajectory has been flown and is being proposed a lot as a way to get cargo to the moon, but this can take 3 or 4 months to get to the moon. So would be less than optimal for humans to go this way.
Yeah, the NASA Grail mission used this several years back when they flew to the moon. They flew 2 spacecraft using this. Of course, the Capstone mission that's now being constructed will use this, and some of the human landing system proposals for putting people back on the surface of the moon are planning to use these types of trajectories to get cargo to lunar orbit.
Yeah. So, and speaking of humans going to the moon, again, the humans wouldn't go here, but the humans are going into another orbit that we mentioned in the last webinar.
While you bring it up, John, I'm not sure if I mentioned this last time or not, but if you're watching this webinar, feel free to write your questions in. We're going to get to as many of them as we can, or that we feel like we can address during this webinar. And if we can't, we'll follow up with you individually afterwards. So write your questions in if you have them for the team. I may have said that twice. I don't remember.
Yeah, well, if they didn't do it the first time, they did the second time. So I'm going to go back to one of the trajectories you showed in the last webinar, and this is a classic halo orbit. That has been used by the Chinese for a communications satellite, and it's a halo orbit because the period in the z-axis matches the period in the xy-axis, and so you kind of get this repeating pattern. So this is a halo orbit because it kind of draws a halo around, around the moon. What we're talking about for where NASA wants to put their next space station, the Lunar Gateway, is in another kind of halo orbit they call a near rectilinear halo orbit. Rectilinear meaning it's practically a straight line. It's very oblong, but it is still a classic halo orbit. But this distance is on the order of thousands of kilometers, like 77,000 kilometers. This distance to the apophis is on the order of like 70,000 kilometers. So this is very different kind of orbit, but it doesn't take as much energy to get into this orbit. And this is classic transfer for getting to the near rectilinear orbit, near rectilinear halo orbit, where you come in kind of on that same near 5-day transfer, but when you get close to the moon, you do a powered gravity assist to slow yourself down here, slows yourself down, and then you make a right-hand turn in space, and you go from this green transfer orbit into this white orbit, and then into the yellow and the blue and the orange here. So this is yet another orbit where the transfer is the same, but you're just not directly capturing here, kind of using 2 maneuvers to capture.
Well, and what John's showing here is interesting too. This is back to what we talked about before. The NRHO that we're going into there is being achieved by doing like a 4-day transfer out to the vicinity of the moon. But there's also trajectories, and back to what I talked before about in terms of the human landing system, there's trajectories that use the ballistic lunar transfer and then transfer into this NRHO. We're not showing an example of that here, but that's another way of doing it. So obviously you can do direct transfers to the moon and get into these kind of halo orbits, or you can do the indirect BLTs and other kind of transfers still to get into the same kind of orbits at the moon.
Yep. So when you're designing these orbits, and I guess we can use this one, but it's very similar to the, I'm just going to bring up the 5-day transfer. Oh, actually, yeah, here's an example where they kind of look the same, like, here, I guess it's closer to the 4.5. They look the same, but you can see that they're in 2 different inclinations, with respect to the Earth. This one is very much out of plane, and this one is closer to the in plane. And they're both going there.
Yep.
You both still get to the moon. But one of the things that when you're on a transfer like this, if the rocket is throwing you here or throwing you here, you've only got 4 or 5 days from when you get taken off the rocket before you have to prepare and do this very large maneuver. So again, your first maneuver, if you're capturing around the moon, is going to be this lunar orbit insertion maneuver. If you're going to the near rectilinear orbit, your first large maneuver is this gravity assist, power gravity assist, and then you have a second maneuver coming up. And one of the differences between an Earth orbiting mission and a lunar mission, and I know we talked about this a little bit in the last webinar, but one of the differences is you really can't miss that maneuver. When you come to the moon, you've got 5 days, and you need to perform that maneuver. You don't really have a mission. So when we're flying geostationary satellites or low Earth orbit satellites, and you get into orbit, satellite goes into safe mode, or you don't feel like doing maneuver that day because you're not ready, you delay it, you go home, go to bed, wake up in the morning, feed the animals, go into work, talk about it, decide when you're going to do the maneuver, and you might put it off until everyone's all ready. When you're preparing for a lunar mission like this, once you launch, the clock is ticking, and you're doing everything in operations, getting ready to do that maneuver, and it needs to be done at that time. So you will reconfigure your satellite so that even if you get certain warnings, you want to get a burn, or at least a decent partial burn, maybe half the delta V at least, if you're going to try to capture. And so the whole philosophy and the pace of operations and the software automation is all different when you're going to the moon. Now, once you're in orbit around the moon, then things ease up again, because you're usually in an orbit where you have a couple days before you have to do a station keeping. So you can think about it, you can delay a maneuver a rev or two, but that's kind of a big difference. Once you launch, it's a different mentality that you have in operations until you perform that capture maneuver, or with the NRHO, until you perform both of these maneuvers.
Yeah, John, and I think that that's an important point too, with respect to navigating one of these types of trajectories. You don't want to have a lot of unknowns other than your spacecraft orbit when you go out and you have these tight operational timelines. Because like you said, the lunar orbit insertion maneuver and even the translunar injection are both really, really critical maneuvers, and you want to have those planned and targeted as absolutely best you can. And to do that, you need to have a good navigation solution to plan off of. And like as well with the NRHO, you talked about coming in on a powered gravity assist, and then very shortly afterwards following that with another maneuver to insert into the orbit. As we know, that anytime you maneuver the spacecraft, you need to go back and recover your orbit accuracy. So you're going to be on a tight timeline there to track, recover your accuracy, possibly calibrate your engines, and be ready to do that next maneuver. So it's a pretty stressful time during the operations.
Yeah, and that's why ahead of time we do a lot of the simulations and even Monte Carlo analysis to characterize those errors and figure out what the system requirements have to be. So we'll take those navigation errors out of orbit determination using simulated data, use that to drive in Monte Carlo to see the variations, and then see when should we correct any deviations within our propellant budget. And that'll you'll do trajectory correction maneuvers along the way to the moon, but they're usually tiny because you need a pretty good launch to do this. And then with your large maneuver, when do you correct it if you only get 80 or 90%? So you end up trying to redesign the trajectory to be more robust, so that if you get launch vehicle dispersions and maneuver execution errors, you can still compensate for it. And it's the only way we know. I think of it like kind of like a submarine where you're on a ship that has, or on a boat with no windows. You know, you're just navigating. The only way we navigate spacecraft is doing orbit determination and tracking data. So if we can't get tracking data, we don't know when to fire the engine. So
Right, and not only that, but it has to be, you know, the tracking data needs to be reliable.
yeah,
And we've all seen missions where, you know, for sometimes days at the beginning of the mission, trying to work out what's going on between the tracking system, the ground software, and the spacecraft. Make sure everything's, you know, flowing properly and the spacecraft's in the right mode to be tracked, and the ground station's properly configured, and we know when we have coherent tracking versus non-coherent tracking, all those kind of things. Whenever you're
it's
on
not like someone can bring up a radar and find you if you're having trouble.
Yeah, exactly.
Well, you know, I know another thing that always fascinates me is the types of scheduling that we had to do when we flew these missions. I know, like on Laddie, we purposely timed the orbit periods of our loops in lunar orbit so that we had the same shifts available when the maneuvers were taking place. So we would have 6-hour or 4-hour orbits and then do maneuvers, you know, in increments of a day to make that happen. And that, you know, you think about that, well, that's not really an orbital mechanics problem. It's a, you know, scheduling problem, but the orbital mechanics will support the scheduling problem, and so you do that. And then we had even more, you know, our friends at Space IL was really interesting. Of course, you know, they didn't want to do maneuvers on Shabbat because that's their religious beliefs, and so they would purposely schedule not to do maneuvers then, and that was a different kind of requirement that we don't typically model in STK anyway, but it was a, you know, that was a requirement for them, so they didn't have any maneuvers, you know, on those kind of days. So it's, you know, all kinds of interesting things that show up, and the orbital mechanics and maneuver planning and those things have to support it.
Yeah. Yeah, and the concept of what maneuvers are critical and what ones you can move and what ones you can't, you end up studying those a lot before the mission launches, and you have to find all the stakeholders in your ground system who care, because you have to find, you know, do you have the ground resources? Is the dish that you're using on Earth going to be pointed at the moon at the time you need it, or do you need a different dish? Different ground networks have different dishes, they have different sizes, different gains. So it's, yeah, scheduling is definitely, you can't understate how important scheduling and coordinating all this is. So
You guys
also
got time for a few questions, or you still have a few more examples that you want to show?
yeah, let's go. Yeah, let's take some of the questions. That'd be good.
Okay, so one of them was, I'm combining a few different questions here that came in, trying to merge them into one, is about low thrust trajectories. And so since transfer duration doesn't really have much of an impact on delta V, can you save any delta V with low thrust trajectories?
Well, so it's an interesting how that question was phrased, because low thrust trajectories will save fuel and mass of the spacecraft. They don't actually save delta V at all. They're more delta V intensive, but you just use much more efficient engines to achieve them. So the delta V, for example, to go from the Earth to the moon, you know, in the trajectories that we showed, are on the order of, you know, 4 kilometers per second, and a trajectory with low thrust might be 6, you know, kilometers per second to get out there. But at the same time, because you can use much more efficient engines, and the, you know, exhaust velocity is much higher for those engines, then the fuel that you have to carry is much lighter, and so the missions can be smaller, and you can get more mass to the moon with the same kind of with the same mass of a propulsion system. So, but the low thrust trajectories are good, but they have the other drawbacks. It takes them a long time to get there. They can be spiraling out, and so if you're spending lots of time spiraling near the Earth, then there's radiation issues that you have to think about for that. And obviously solar radiation, typically those missions have high power requirements, and so they have large arrays that have to be pointed at the sun, and that's problematic because you have to unfurl those, and if you're a small spacecraft, then get things unfurled is more complicated. So, you know, there's certainly ways to do that, and people who have thought about that.
Well, and then there's the eclipses. I mean, you've got, the moon, as we know with lunar eclipses and solar eclipses, sometimes the Earth blocks the sun from the moon and vice versa.
So but the Smart 1 mission from Europe flew to the moon using low thrust, and then there's some other planned missions now that are looking at that. The PPE, power propulsion element for NASA's human systems at the moon, being built by Maxar. That's a low thrust system and based on a Maxar bus, and that'll be using low energy trajectories to get out and get into the moon. And maybe even a ballistic transfer, where the spacecraft will be launched on a ballistic transfer and then use low thrust to capture into the moon. So that's a combination. We didn't show low thrust trajectories, but we showed a ballistic transfer. Imagine injecting the whole spacecraft onto a ballistic transfer, and now the low thrust thing captures at the moon, which is nicer for it because the delta V requirements to capture are low. So lots of stuff to think about in the low thrust, but that's low thrust is a whole other topic that we'd probably have to do in a different seminar.
Gotcha. Okay. Well, thank you for that. Another question here. How do you mitigate the challenges posed by the sensitivities of such a highly nonlinear design space? I believe it was talking about, there's a note in there about the 3-day versus the 5-day. Is that something you guys can get into, or is it something we should do an individual follow-up for?
Yeah, I mean, there's a little bit to think about. I guess the way that I think about it is people will say to me sometimes, and they hear what they do, oh, you must be great at math and all these kind of things. And really in the software, you can do a lot of these things visually. And you talk about nonlinearities and of course, we deal with nonlinearities all the time. I mean, throwing a baseball or catching a football or shooting a basket, jumping up on a step. We do nonlinear things in our brain all the time. So the neat thing about software like SDK that lets you visualize these things is it lets your brain do what your brain already does. Your brain can see derivatives and can see when nonlinearities exist and compensate for them. And so a lot of times in here, while there's mathematics and stuff certainly in the software, we're using just the intuition and the visual nature of the software so that you can kind of eyeball things close to where you want. And there's an awful lot of that can be done in this software that I think is important. And we use that all the time in our designs to try to, if we know a trajectory exists, we can kind of eyeball something that gets close and then let the numerics go over and kind of drive it in. But
so you're kind of implying that the graphics are analytical.
Sure. But they give you an intuition that visually that your brain can make use of, because your brain does nonlinear stuff all the time. We know how to do that, without thinking about it, without calculating stuff. And so the graphics give you a combination of precise numerics as well as a graphical representation of a problem that your brain can wrap itself around and gain an intuition for. So after a while, you start to see the rotating coordinate frames and these kind of things. And I had a mentor of mine, Chauncey Uphoff, that described things to me before I had these kinds of tools, because he could see this stuff in his head because of years of practice. And he would try to describe it to me, and I didn't know how to see it in my head because I hadn't seen it visually and didn't have the acuity with that he did. But once I had the software, then I could start to see the things that he talked about. So we have a leg up on him because we have these tools that allow us to cheat a little bit and get an intuition in a way that he didn't have available to him. But there are nonlinearities, but like I say, the graphics really allow you to see it. You can see when wrong things are happening.
And one of the things that when we started the swing by program at NASA Goddard in 1989, Josh, that you were mentioning earlier, we saw that right away. As soon as we put the graphics in, and as Mike mentioned, you can see the derivatives, you can see the temporal and the spatial derivatives. We were able to train so many more orbit analysts to design these nonlinear trajectories once they could see what it was, because the Keplerian elements don't really work for you, but we don't have a great representation in a 3 and 4 body trajectory. But as Mike said, the human just gets it right away. They see the trajectory and they go, oh, that one went to the left a little bit faster.
Right.
And if I adjust this maneuver, it goes more to the right and it slows down.
Yeah, and that's what John means when he's talking about seeing the derivatives. We're not visualizing, symbolic, calculus notation in our heads or anything. You're just looking at it. You're like, oh, you throw a baseball, it curves off to the right. I see the trajectory curves off to the left here, or it's running into the moon. If I tweak it a little bit this way, it won't. So that's the that's the kind of thing that I think that this software really lends itself well to, is letting you see things and get an intuition for these problems, because the nonlinear stuff, your brain can do it.
And once we do that, and we get an intuition for the nonlinearities and what things control it, we're not good enough to type the numbers in, but that's when we put it into the targeter. And that's what we always say about Astrogator's targeter. It's only doing things that you could do if you were patient enough and had enough time. So it will start varying the things for you. And to control the nonlinearities, we put kind of some fairly simple controls on it, like a maximum step size, so that it never jumps. Every step that it takes is kind of a linear step, and you take a bunch of short linear steps to get a curve. So, but it really, the numerical algorithms that we have in Astrogator, a lot of those come from a long time of building up an intuition. You figure out how you'd like to do it by hand, and then you go into Astrogator, and then you say, okay, I varied this and I saw this happen. Now you vary that. Take your time. Go ahead, take 100 steps if you want to, and you'll get there. And that's been extremely powerful.
So it's kind of like you guys see the green code in the Matrix.
No, it's not like that. It's kind of like it's kind of like Field of Dreams when you're playing catch with your dad, right? It's like, you throw a baseball, you know how to throw a baseball. When you see these trajectories, you'll see them again, and you'll know how it is. And it's not the Matrix. It's pattern recognition stuff. It's really, not this high priest thing. You start to visualize, and with, when you're solving problems like this, you make a lot of big, screens, and you have big monitors, and you're allowing yourself to see as much as possible. So you get an intuition for the problem, and you know what it looks like, and you know what doesn't make sense physically. And so if you see a non-physical thing, a left hand, right, 90-degree turn in space, you're like, okay, something's going on there. If you see the trajectory running through the middle of the Earth and then it veers off into deep space, you're like, okay, that's wrong. And and you can see something coming over the top of the moon or the bottom. Oh gosh, I didn't set up the nodes right. So there's, you get an intuition for these problems by looking at them, just like you would any other thing that you do in your life. If you were building things or throwing a ball or, riding a bike or whatever it is, you get an intuition for it having done it. And it's the same way here.
Very cool. I just wanted to work at a Matrix reference, but you shut it down pretty hard, but that's okay. I got one more question.
John might be the Matrix, but I don't visualize that.
Right. All right. So I got one more question for you guys here. Okay. So when you're doing the trajectory design from the Earth to the moon and the Earth-Moon systems, there's different force models you can use. When do you decide which ones to use? Which one's the primary? When do you switch? Questions along that line. Do you have any advice for that?
Yeah, so there is, let's talk about when is the orbit Earth-centered and when is it moon-centered? So the short answer is there is no one right answer. The mental model that a lot of us have from looking at textbooks and whatnot is if you're going from Earth to Mars, you are in Earth orbit within the Earth's sphere of influence. You leave the sphere of influence and you're a sun-centered orbit, heliocentric. And then when you get close to Mars and you enter Mars's sphere of influence, you become a Mars-centered orbit. And you calculate the spheres of influence based on the dominant gravity model at the time.
And that being said, that was a really important thing when we used to calculate trajectories as a series of patched conics, where it was a two-body orbit from the Earth, and then after a while it became a two-body orbit with respect to the moon. And so when you were doing it that way, when you were constrained by that kind of calculation, then you cared about where the transitions were. When you're numerically integrating, and you're numerically integrating with respect to the Earth and the force model there, and you're going towards the moon, and you're numerically integrating the lunar perturbations, it's not as sensitive, and it doesn't matter as much where you hand off. At some point, the gravity things and the stuff that you model will start to matter in operations. But a lot of times in preliminary stuff, when we're calculating trajectories, we don't have all the gravity.
And one of the problems is because the moon's gravity is so large compared to the Earth's gravity, you're always being influenced by both.
Right.
So you can calculate a sphere of influence of the moon, and it doesn't really help on the Clementine mission. So when we launched in 1994, in January 94, using swing by, the state of the computer then was that we stayed Earth-centered the entire time until we got to the moon. And then when we did lunar orbit insertion, we switched to moon-centered. And a lot of that was just for computational efficiency, that evaluating the spherical harmonics of the moon's gravity is not efficient and it would slow down the targeter. Computers are a lot faster. Mike, I think on LADI, we stayed Earth-centered till we got about 50,000 kilometers away from the moon.
Right.
With the trajectory design. However, when we were doing orbit determination on LADI, something else completely different happens. So we were in some phasing loops. So we're in Earth orbit for about a month. We go through our final perigee, and then when we were on this final 5-day transfer, I'm just going to show the 5-day transfer, because that's like the final leg of LADI. We were Earth orbit determination all the way, and so we let the orbit determination filter always be Earth-centered the entire way. However, we knew once we got to the moon, we needed to be moon-centered, and we didn't want to restart the filter right when we got to the moon. So we started a second filter just about a day away from the Earth. It was moon-centered. We ran 2 copies of ODTK, one Earth-centered and one moon-centered, and kept comparing the solutions so that we used the Earth-centered solution as a seed for the moon-centered orbit state and uncertainty, and ran both of them simultaneously. And then when we got to the moon, we could drop the Earth-centered one and just go moon-centered. So one of the things that you do for trajectory is different than you might do for orbit determination. So a lot of it is the efficiency of how fast the computer is that you're running on. And then why do you need to switch? If you're using a Kalman filter and you want to daisy chain yourself. But like Mike said, for early analysis, to get first, or even better than first order numbers, you can stay all Earth-centered here.
Yeah, I mean, and, you know, we've even seen on some projects where, you know, certainly when you start to get into lunar orbit and then you start to do really low lunar orbit stuff and frozen orbits and those kind of things, then it gets really important what the gravity fields are that you have on and that. But you can do an awful lot in cislunar space with point masses and it'll be pretty close to the truth.
Yeah,
and not
it is important to have the real position of the moon, though.
Right, right. But I mean, if you had the point mass of the Earth and the point mass of the moon, it isn't that wrong. I mean, if you're going into orbit around the moon, it starts to get wrong pretty quick. But if you're just flying by the moon and doing something, it's not bad.
And you need the point mass of the sun too.
The same with the Earth. It depends on how long you're going to be close to the Earth and how, you know, and how low you're going to be. You know, if you're just leaving the Earth on an asymptote to to Mars or the moon or something, the gravity field at the Earth doesn't have much time to do anything. And the same with the moon. As you're flying by at high speed, if you're just doing a flyby, you know, but if you're going to orbit and starting to get low, gravity field's got to be on. And then how much gravity field do you have to model? Well, if you're just doing analysis, it's one thing. If you're, you know, if you're flying it, okay, you know, now you got to match up your OD.
Or if you're doing orbit determination air analysis, I mean, you have to be above 150 by 150 for low lunar orbits, just even to get the analysis right to calculate the uncertainties. You know, the Grail mission has now got a great gravity model of the moon, and we know those uncertainties. But we've seen, you know, at SEE, we've seen big differences in the errors due to the omission of the field if we don't get, you know, 150, 150 or 200 by 200 up there. And the computers are fast enough that it doesn't slow it down like it used to, you know. Pour a little liquid nitrogen on your keyboard periodically. And
I guess the other thing is that the question was, you know, how do you decide which forces to use? When you're doing analysis stuff, it's really kind of about what you remember. Like if we're going to the moon, when we're near the Earth, we're probably not going to do anything more than like an 8x8 field, just because we're not there for very long. If we were in low Earth orbit for a long time, that'd be different. You know, at GEO, there's some other thing that they do. When we get, you know, closer to the moon, at some point, like John said, 50,000 or 20,000 or something, you can decide to switch over, and those numbers are right as long as you've got, you know, the force. The Earth and the sun, or Earth and the moon and the sun in there. And then once you get the lunar orbit, then you start making maybe a 20 by 20 field or something. But operations and other things, then it matters.
Well, the cool thing that AGI put into Astrogator several years ago was that you can put in the spherical harmonics of the Earth and the Moon at the same time in Astrogator. So one of the things we did in preparation for LADEE to answer this question is we just started doing studies. And we started parametrically varying the force models to see when it mattered. I think we ended up with a 21 by 21 around the Earth. And at the time, it might have been like 100 and 100 around the Moon. But you take Astrogator and you run it with different sets of force models. And you see, are the differences matter? If I go from an 8 by 8 to 21 by 21, do I see a difference? 21 by 21 around the Earth to 50 by 50, do I see a difference? If not, you back off for speed. And
But
so
in-
those, prior to launch, you do a lot of those kind of studies.
The trajectories that we showed today, there's no 21 by 21s anywhere in there. There's probably
Right.
8 fields in there and point masses everywhere, and it's all
Yeah,
good.
and the delta V's will all be the same.
Yep.
Really where we see it mostly is when we want to match the trajectory design with the orbit determination. That's where we really start caring about the force models. And like Mike said, you need that for operations. But
That's really important, because if you don't have the force models right in your propagation, then you start seeing things that turn up as noise when you really know the numbers. So you should put the right things in.
And
Yeah,
you,
and then-
you trajectory design types are famous for not using solar pressure too.
I was just going to say solar radiation. You stole that from me, Jim.
What was the
Yeah.
one we were on the other day, John, where we actually had solar radiation pressure turned on, but solar gravity turned off, right? So that was a thing in a particular mission design that we had, where the sun was giving us radiation pressure, but not gravity in that simulation.
Yeah. Actually, that's a good point. And you had mentioned before, you can get away with point mass of Earth and point mass of Moon, but really you should be turning on the point mass of the sun too, because
Yeah,
it takes more work to prove you don't need it than when you do. But then you get the arguments with, should you throw on Jupiter and Saturn as well?
right, yeah.
It's too bad we don't have a way to calculate the effect using some sort of inverse square law or something. You might be able to.
Yeah, exactly. No, you can't.
figure it out.
No, we've had missions. I think there was a libration point mission we worked on, John, on WMAP, where we did have discussions about whether Neptune needed to be turned on or not. And
Yeah.
certainly,
Well, in the Earth sun libration points, they started becoming on the order of other accelerations.
certainly in the Earth Sun libration point missions, you did have to think about Venus and Jupiter. We're both very important, and then the other planets were, Neptune I think was a little bit much, but I think we did have it turned on. But certainly Jupiter and Venus were measurable.
Yeah, and so really the answer to your question is you do parametric studies ahead of time, see which ones really have an effect and what the variation is going to be, and then you want the force models more accurate than your orbit determination accuracies by an order of magnitude or quite a bit more.
Or you remember what you did last time, or the guy you're working with remembers what he did last time, and so you don't have to do it.
Right, except if they didn't have a good reason for doing it.
That's right. You could have made it up.
Right. Personally, I still like turning on the gravity of Pluto just because it is a planet. So
Not a political discussion.
Yeah, we don't have time for that one.
That square and.
Well, thank you guys very much. Can you give us a little bit of insight into what we're going to see in future webinars in this series? Nothing too
Probably.
long, just a little bit.
I'm sure we could.
If we do it,
All right. So we'll
Personally,
probably
I'd like
cover.
to talk about navigation.
Oh, yeah. Oh, I don't know about that.
navigation maneuvers.
We
What else?
wanted to get into some of the differences between some of these textbook type trajectories I've been showing you and then the operations. Because you will do things a little bit different in operations when you're thinking about the physical constraints of the hardware. And as Mike mentioned, the human life cycle. So the
Great.
trajectories actually will look different.
Great. Well, thanks. Everybody got the questions in. If we didn't get your questions, we'll follow up with you individually. And we look forward to seeing you guys in the next webinar.
Cool.
All right, thank you.
Yep, guys.
Goodbye,
Talk to you
everybody.
soon.
All right.